Greetings, everyone. This particular video is going to focus on talking about motion once again, but also focusing on a new way that we can map out motion besides the things we talked about before. The idea of a motion map, which remember is the little dots we put on the screen, and a position time graph, which you kind of see over to the right, or just collecting data in general. So you'll notice that I have put in a video in Vernier, and I've actually taken the time to go through and analyze it. Now, I've already clicked the dots, so I'm just going to move forward, and you can see kind of where I placed my dots. And kind of what we can see from all this is just by looking at it, it's pretty obvious that this appears to be going at some sort of constant velocity. All right, and we're going to ask multiple questions why it is that. We're looking at the idea that the spacing between the points is pretty similar. Looking at the graph, that seems to have a pretty linear trend, and if I go through and I try to see if there's a linear fit, it looks pretty close. All right. Now, the other way that we can do this, and the new way we can graph it, is we don't necessarily have to just graph the position of the car. Another thing we can do is we can actually map out how fast an object, in this case the car, is moving as well. Because just like it's important to kind of know things like where the car is, it might be really useful too to have some sort of situation where we can easily see how the velocity might be changing as a car is moving. All right. Now, what we do is we produce a graph that we refer to as it measures the velocity versus time. All right, and that's exactly what we're going to do here. So in fact, I can actually turn on the x velocity. And what happens is that this graph actually shows me now two things. The red dots are representing where the car is. The yellow dots are representing the velocity, how fast this car is actually going. And actually, just to make this a little bit easier so it matches up, let's set the scale as well. Perfect. All right. Now, with that being said, looking at this graph, what matters here is that we can clearly see that we have a very interesting graph to kind of look at. Now, I do apologize, the graph, there we go, all scaled. The reason this matters and the reason this is important is because now we've actually created an entirely new graph that we can use to kind of map out the motion. Now, in this case, this car is going at a constant velocity, which means is I'm actually graphing how fast it's going every little time interval. If it's going at a constant velocity, it shouldn't be changing. So you'll notice that these yellow dots seem to almost make a horizontal line. All right. And the fact of the matter is, that is telling us that this is actually going at a constant velocity because it's not changing when we read the graph. No matter what time it is, the velocity seems to be just about the same at all these points, give or take just a little bit of air. So, the reason I bring that up is because this video is going to focus on kind of a couple different types of graphs that we can use to model motion. So we're kind of putting all the pieces together to talk about motion here. All right. So if you could, you need to open up the note sheet that goes with this video. You'll see it on Canvas because we're going to be drawing some stuff today. So what we have here is we have a couple different spaces. What we're going to end up doing is we're going to actually have three different types of motion graphs that we can use to model the motion of something. Now, this particular note sheet has it labeled Unit 1, which is constant velocity model. That's for things that are moving at a constant velocity. And then the Unit 3, the order was weird in this particular unit, where it talks about things that might be accelerating, which means they're either speeding up or slowing down. All right. Now, what we're going to do is we're going to actually draw the graph that shows this type of motion in each one. All right. So the first thing we're going to do is we're going to look at position time graphs. Now, we've been talking about position time graphs the most right now. This is the only type of graph we have created. And remember, all this graph does is basically tell me where I am. And in fact, that's exactly what I've written right here. It says the graph tells me where I am at any point in time. All right. Another important piece of it is that looking at this graph, the slope of whatever line you're looking at in a position time graph represents the velocity of an object. All right. Now, right here, this is going to be nice constant velocity because it is a linear, just like we've seen before. If we're looking at things that are speeding up or slowing down, which means accelerating, the graph looks slightly different. So in this case, drew a graph for an object that is speeding up in the positive direction. Right? And we've done this before. We've practiced it multiple times. We saw this in our lab. Whenever we have that, it looks like the graph would be getting steeper and steeper. And the reason is because if we're mapping out just the position dots are getting farther and farther apart as we're kind of drawing that graph. Now, because the graph is getting steeper, it means it's speeding up in this case. If it was getting less steep, something like that, it's kind of traced with my mouse, that would mean it was slowing down. All right? And again, all this type of graph does, this position time graph, just tells me where I am and at what time I'm at that position. Now, for the next new graph. Again, this is kind of what we just talked about over here in the Vernier analysis, something referred to as a velocity versus time graph. So what this graph measures is how fast I'm going and in what direction at any point in time. All right? It would be kind of the equivalent of that if you were looking at data if you were at some NASCAR event or whatnot, and you were constantly seeing how fast the car was going with respect to the time it was moving at that speed. That's basically what this graph does. All right? Now, these graphs look slightly different depending on what's going on. For a velocity time graph that is a constant velocity, it will always be a horizontal line, all right? Because the velocity is not changing. Now, it might not necessarily always be zero because it might not be at zero, but in this case, this is just showing an object that's going at some constant velocity. It's reach some cruising speed, maybe it's going the speed limit, but it will be consistently horizontal because it's never changing as long as this type of motion happens. If we're talking about accelerated motion, however, something different happens. If an object is speeding up, the velocity is actually increasing, which means that according to the graph, I need to show changing velocity. Now, the way to do that, we're going to find out, is to just basically draw some sort of diagonal line like this. But the way the diagonal line goes is actually going to dictate if it's speeding up or slowing down. The way I've drawn this one right now is, again, for an object speeding up in the positive direction. So this is showing that because the velocity number is getting bigger. All right? It's also moving in the positive direction. The same thing is true if I asked you to draw a velocity time graph that's going in the negative direction. If I have an object that is speeding up in the negative direction, like the fan cart in the lab, what I would draw is a line that was going like this. And what that would tell me is that, one, it's going in the negative direction because it's on the negative side of the graph, but it's getting faster because the number is getting bigger. This is where that idea of positive and negative really becomes very important, because we want to be very clear that just because something is on the negative side of this graph does not mean it's smaller than something on the positive side. All right? But again, for velocity time graphs, and we'll keep practicing this, I promise, it's just kind of the intro into it. If it's constant velocity, the graph is going to look like a horizontal line. If it's accelerating, the graph is going to look something like that, where it may or may not be linear, to kind of signify that the velocity is changing. All right? Then the third and final thing that we can do as well, and we don't use this too much, but it's something that we could see, especially we're going to find out it's important when we talk about maybe impacts and collisions, is the acceleration versus time graph. Now, just like this one measured where I am with respect to the time, this one's how fast and the direction I'm going in with respect to the time. This is basically measuring how much acceleration I'm experiencing with respect to the time. All right? Now, for constant velocity, acceleration time graphs are super easy, because when something's moving at a constant velocity, it has no acceleration because it's not speeding up or slowing down, which means its acceleration is equal to zero. That means it's really super easy to draw the graph, because if it's got a constant velocity, the acceleration is zero, so it's just a horizontal line right here on zero. All right? Now, the interesting part happens when we get to something that is accelerating. If an object is speeding up or slowing down, we can write it like such a way that it measures its acceleration. All right? Now, for our intents and purposes, we're not super concerned about what acceleration looks like. We're going to make the assumption that acceleration is always constant in here. So basically, we're not going to have weird little graphs that pop up in this. And we're going to practice this one a lot more in the future. So we're not super worried about it right now. The only thing that matters for an acceleration time graph at the moment that we care about is the idea that acceleration could also be positive or negative. We're going to find out that acceleration actually has a direction just like all the other ones. But it's going to make a lot more sense when we start to talk about forces, what exactly that means. All right? So, the main takeaway here is this new type of graph referred to as the velocity time graph. The velocity time graph tells me how fast I'm going and in what direction I'm going in. All right? And if it's accelerating, it's not going to be a horizontal line, it's going to be some sort of diagonal line. All right? So, with that being said, there's going to be a couple of assignments I need you to work through on Canvas that kind of relate back to this as well. There's also a daily quiz you're going to need to answer to kind of make sure you watch this video, ask a couple questions about this and some of the stuff we talked about earlier this week. So with that being said, if you have any questions, please don't hesitate to send me an email or come to his office hours. Otherwise, have a great rest of the day.